This object is smaller than we thought, but it's doing far more than its size should allow. New analysis brings together imaging, photometry, and simple dust dynamics. And when you line those pieces up, a clear picture starts to form. 3i Atlas is compact, sub-kilometer, yet it's driving a narrow, persistent structure aimed straight toward the sun. That's what we're going to unpack. This figure is the backbone of the paper. Top row. First, you're seeing the object split into R, G, and B channels. In red and green, the inner environment is elongated and tightly collimated. In blue, that extension collapses. That color behavior matters. Red and green trace dust scattering. Blue is dominated by gas emission, which stays compact. So this long sunward feature is not gas, it's dust. Now the bottom row on the left, the Larsonina filter removes a smooth coma and enhances directional structure. What's left is a single narrow jet extending tens of thousands of kilometers. It's not symmetric, it's not random, and it's not an image artifact. The annotations show the jet length pushing approximately 70,000 kilometers, a line near a fixed position angle. That stability across processing methods is key. If radiation pressure were in control, this structure would sway or bend quickly. Instead, it stays focused, which tells us something important before we even touch equations. The dust had to leave fast, much faster than typical coma models allow. This single image already forces two conclusions. The activity is highly localized, not global. The outflow is energetic and directed, not passive. That's where the rest of the paper goes next. This is where gravity alone stops working. When astronomers reconstructed the trajectory of 3i Atlas, they found something subtle but real. The path doesn't follow a purely gravitational curve. There's a small persistent acceleration layered on top of gravity, not noise, not a fitting error, a real force. What matters most is the direction. That extra push is aligned sunward, exactly where you'd expect recoil from material leaving the surface. This is the same basic signature seen before in other interstellar visitors. But here, the effect is stronger. Near perihelion, the measured acceleration is about 3 by 10 - 5 meters per second squared, roughly an order of magnitude larger than what was inferred for one eye. That immediately rules out passive explanations. Radiation pressure alone isn't enough, and random mass loss wouldn't stay aligned as cleanly. What this slide tells us is simple but powerful. Something on 3i Atlas is acting like a thruster, localized, directional, and sustained over time. That raises the next question. If there's a real force, what's generating it? Once the extra force is established, the question becomes straightforward. What could produce a steady, sunward-aligned push like this? The leading idea is recoil from material leaving the surface. Ice is heated by sunlight transition directly from solid to gas. When that gas escapes in a preferred direction, the object is pushed the other way. That's basic physics. No assumptions beyond conservation of momentum. But not all volatiles behave the same. This slide shows what the authors tested. Carbon monoxide, carbon dioxide, ammonia, methane. Each one sublimits at different temperatures. Each one produces a different amount of thrust at a given distance from the sun. And that distance matters. The anomaly is measured between 1 and 2 astronomical units. That immediately rules out anything that only becomes active much closer in. So the problem becomes quantitative, not speculative. Can any common volatile produce the observed acceleration of the measured distances without requiring an unrealistically large active surface? That's what the thermophysical model is designed to answer. And when you run those numbers, something interesting happens. Only one candidate survives the test. When the models are run, there's no ambiguity. Only one volatile works. At distances between 1 and 2 Australian dollars, carbon monoxide produces enough thrust to match the observed acceleration. Everything else falls short. Carbon dioxide, ammonia, methane all decline too quickly. All are too weak at these temperatures. CO stays efficient where the anomaly is measured. That's why its curve sits above the rest. So the source of the push isn't exotic. It's specific. A localized carbon monoxide-driven outflow. This is a consistency check. The question here is simple. Where does the sun's energy go? If energy goes into sublimation, you get thrust. If it's re-radiated as heat, you don't. That balance is what this ratio shows. For carbon monoxide, the surface stays sublimation dominated across the entire range. Energy keeps turning into gas. Gas keeps producing recoil. Everything else drops into the radiative regime. So, this isn't just about volatility, it's about efficiency. CO doesn't just work, it keeps working. At this point, the picture closes. The measured acceleration and the modeled force line up about 3*105 MOS squared. The numbers agree. No exotic physics is needed. No unusual assumptions. A localized outflow driven by carbon monoxide is enough to explain the push. Other candidates simply can't do it. They don't sublimate efficiently enough. They don't transfer enough momentum. So the force acting on 3I Atlas isn't mysterious anymore. It's directional. It's sustained and it's physically ordinary. What makes it interesting isn't what it is. It's how strong it is for something this small. Now, the physics shows up in the images. This structure isn't inferred. It's visible. Deep processing reveals a narrow, highly collimated jet pointing toward the sun. An anti-sun tail would be expected. This is the opposite. The jet stays tight for around 70,000 kilometers. Split by color, the story gets clearer. In red and green, the feature is strong and continuous. In blue, it largely disappears. That color behavior matters. Red and green track dust scattering. Blue is dominated by gas emission. So, this isn't a gas plume. It's a dust-loaded jet, and it's the visible signature of the same directed outflow driving the acceleration. This is the full portrait. At the center is a tiny nucleus only a few hundred meters across. By itself, that shouldn't be enough to do much. But it's not acting alone. The motion is driven by localized carbon monoxide power jets, not global activity, not uniform loss. These jets are efficient enough to do two things at once. They push the object measurably off its gravitational path, and they launch dust at tens of meters RS, forming a long, narrow, sunward structure. The activity looks extreme because the source is small. An extended cloud of icy grains in the surrounding coma boosts the total output. That's why the object appears hyperactive relative to its size. And the composition matters. A coal-rich makeup points to formation in a very cold environment far from the inner regions of its original system. Material that stayed cold, undisturbed, and chemically primitive. So what we're seeing isn't a mystery engine. It's a small body with a very efficient one. The real question now is this. How common are objects like this in the galaxy? If you want to keep following what 3i Atlas is still teaching us, like the video, subscribe, and share it with someone who cares about how real data reshapes big ideas.